An operational amplifier is a DC-coupled high-gain electronic voltage amplifier with a differential input and, usually, a single-ended output. In this configuration, an op-amp produces an output potential that is typically hundreds of thousands of times larger than the potential difference between its input terminals. Operational amplifiers had their origins in analog computers, where they were used to do mathematical operations in many linear, nonlinear and frequency-dependent circuits. Characteristics of a circuit using an op-amp are set by external components with little dependence on temperature changes or manufacturing variations in the op-amp itself, which makes op-amps popular building blocks for circuit design. Op-amps are among the most widely used electronic devices today, being used in a vast array of consumer, industrial, and scientific devices. Many standard IC op-amps cost only a few cents in moderate production volume. However, some integrated or hybrid operational amplifiers with special performance specifications may cost over $100 in small quantities. Op-amps may be packaged as components, or used as elements of more complex integrated circuits. The op-amp is one type of differential amplifier. Other types of differential amplifier include the fully differential amplifier, the instrumentation amplifier, the isolation amplifier, and negative feedback amplifier. Circuit notation. The circuit symbol for an op-amp is shown to the right, where V plus non-inverting input, VAR inverting input, VOUT, output, versus plus positive power supply, VS a negative power supply. The power supply pins can be labeled in different ways. Often these pins are left out of the diagram for clarity, and the power configuration is described or assumed from the circuit. Operation. The amplifier's differential inputs consist of a non-inverting input with voltage V+ and an inverting input with voltage VAR. Ideally, the op-amp amplifies only the difference in voltage between the two, which is called the differential input voltage. The output voltage of the op-amp VOUT is given by the equation, where AOL is the open loop gain of the amplifier. Open loop, the magnitude of AOL is typically very large, euro 100,000 or more for integrated circuit op-amps euro, and therefore even a quite small difference between V+ and VAR drives the amplifier output nearly to the supply voltage. Situations in which the output voltage is equal to or greater than the supply voltage are referred to as saturation of the amplifier. The magnitude of AOL is not well controlled by the manufacturing process, and so it is impractical to use an operational amplifier as a standalone differential amplifier. Without negative feedback, and perhaps with positive feedback for regeneration, an op-amp acts as a comparator. If the inverting input is held at ground directly or by a resistor G, and the input voltage VAN applied to the non-inverting input is positive, the output will be maximum positive. If VAN is negative, the output will be maximum negative. Since there is no feedback from the output to either input, this is an open-loop circuit acting as a comparator. The circuit's gain is just the AOL of the op-amp. Closed loop. If predictable operation is desired, negative feedback is used, by applying a portion of the output voltage to the inverting input. The closed-loop feedback greatly reduces the gain of the circuit. When negative feedback is used, the circuit's overall gain and response becomes determined mostly by the feedback network, rather than by the op-amp characteristics. If the feedback network is made of components with values small relative to the op-amp's input impedance, the value of the op-amp's open-loop response AOL does not seriously affect the circuit's performance. The response of the op-amp circuit with its input, output, and feedback circuits to an input is characterized mathematically by a transfer function. Designing an op-amp circuit to have a desired transfer function is in the realm of electrical engineering. The transfer functions are important in most applications of op-amps, such as in analog computers. High input impedance at the input terminals and low output impedance at the output terminal, S, are particularly useful features of an op-amp. In the non-inverting amplifier on the right, the presence of negative feedback via the voltage divider RF, RG determines the closed-loop gain ACL equals VOUT/VAN. Equilibrium will be established when VOUT is just sufficient to reach around and pull the inverting input to the same voltage as VAN. The voltage gain of the entire circuit is thus 1 plus Rf Rg. As a simple example, if Van equals 1 of V and Rf equals Rg, Vout will be 2 of V, exactly the amount required to keep Vout 1 of V. Because of the feedback provided by the Rf, Rg network, this is a closed-loop circuit. Another way to analyze this circuit proceeds by making the following assumptions. When an op-amp operates in linear mode, the difference in voltage between the non-inverting pin and the inverting pin is negligibly small. The input's impedance between AND pins is much larger than other resistances in the circuit. The input signal Van appears at both AND pins, resulting in a current I through Rg equal to Van Rg. Since Kirchhoff's current law states that the same current must leave a node as enter it, and since the impedance into the pin is near infinity, we can assume practically all of the same current I flows through Rf, creating an output voltage. By combining terms, we determine the closed-loop gain ACL. Op-amp characteristics, ideal op-amps. An ideal op-amp is usually considered to have the following properties: infinite open-loop gain G equals Vout/Van, infinite inputs impedance Rin, and so zero input current, zero input offset voltage, infinite voltage range available at the output, infinite bandwidth with zero phase shift and infinite slew rate, zero outputs impedance route, zero noise, infinite common mode rejection ratio, infinite power supply rejection ratio. These ideals can be summarized by the two golden rules. I. The output attempts to do whatever is necessary to make the voltage difference between the inputs zero. 2. The inputs draw no current. The first rule only applies in the usual case where the op-amp is used in a closed-loop design. These rules are commonly used as a good first approximation for analyzing or designing op-amp circuits. None of these ideals can be perfectly realized. A real op-amp may be modeled with non-infinite or non-zero parameters using equivalent resistors and capacitors in the op-amp model. The designer can then include these effects into the overall performance of the final circuit. Some parameters may turn out to have negligible effect on the final design while others represent actual limitations of the final performance that must be evaluated. Real op-amps differ from the ideal model in various aspects. DC imperfections. Real operational amplifiers suffer from several non-ideal effects. Finite gain. Open-loop gain is infinite in the ideal operational amplifier but finite in real operational amplifiers. Typical devices exhibit open-loop DC gain ranging from 100,000 to over 1 million. So long as the loop gain is very large, the circuit gain will be determined entirely by the amount of negative feedback. In cases where closed-loop gain must be very high, the feedback gain will be very low, and the low feedback gain causes low loop gain. In these cases, the operational amplifier will cease to behave ideally. Finite input impedances. The differential input impedance of the operational amplifier is defined as the impedance between its two inputs. The common mode input impedance is the impedance from each input to ground. MOSFET input operational amplifiers often have protection circuits that effectively short-circuit any input differences greater than a small threshold, so the input's impedance can appear to be very low in some tests. However, as long as these operational amplifiers are used in a typical high-gain negative feedback application, these protection circuits will be inactive. The input bias and leakage currents described below are a more important design parameter for typical operational amplifier applications. Non-zero outputs impedance. Low outputs impedance is important for low impedance loads. For these loads, the voltage drop across the output's impedance of the amplifier will be significant. Hence, the output's impedance of the amplifier limits the maximum power that can be provided. In configurations with a voltage sensing negative feedback, the output's impedance of the amplifier is effectively lowered. Thus, in linear applications, op-amps usually exhibit a very low output's impedance indeed. Negative feedback cannot, however, reduce the limitations that are LOAD in conjunction with route place on the maximum and minimum possible output voltages. It can only reduce output errors within that range. Low impedance outputs typically require high quiescent current in the output stage and will dissipate more power, so low-power designs may purposely sacrifice low output's impedance. Input current, due to biasing requirements or leakage, a small amount of current for JFET input stages, and only a few picoampere for MOSFET input stages, flows into the inputs. When large resistors or sources with high outputs impedances are used in the circuit, these small currents can produce large unmodeled voltage drops. If the input currents are matched, and the impedance looking out of both inputs are matched, then the voltages produced at each input will be equal. Because the operational amplifier operates on the difference between its inputs, these matched voltages will have no effect. It is more common for the input currents to be slightly mismatched, and so a small offset voltage can be produced. This offset voltage can create offsets or drifting in the operational amplifier. It can often be nulled externally. However, many operational amplifiers include offset null or balance pins and some procedure for using them to remove this offset. Some operational amplifiers attempt to nullify this offset automatically. Input offset voltage. This voltage, which is what is required across the op-amp's input terminals to drive the output voltage to zero, is related to the mismatches in input bias current. In the perfect amplifier, there would be no input offset voltage. However, it exists in actual op-amps because of imperfections in the differential amplifier that constitutes the input stage of the vast majority of these devices. Input offset voltage creates two problems. First, due to the amplifier's high voltage gain, it virtually assures that the amplifier output will go into saturation if it is operated without negative feedback, even when the input terminals are wired together. Second, in a closed-loop, negative feedback configuration, the input offset voltage is amplified along with the signal, and this may pose a problem if high-precision DC amplification is required or if the input signal is very small. Common mode gain. A perfect operational amplifier amplifies only the voltage difference between its two inputs, completely rejecting all voltages that are common to both. However, the differential input stage of an operational amplifier is never perfect, leading to the amplification of these common voltages to some degree. The standard measure of this defect is called the common mode rejection ratio. Minimization of common mode gain is usually important in non-inverting amplifiers that operate at high amplification. Power supply rejection. The output of a perfect operational amplifier will be completely independent from ripples that arrive on its power supply inputs. Every real operational amplifier has a specified power supply rejection ratio that reflects how well the op-amp can reject changes in its supply voltage. Copious use of bypass capacitors can improve the PSRR of many devices, including the operational amplifier. Temperature effects. All parameters change with temperature. Temperature drift of the input offset voltage is especially important. Drift. Real op-amp parameters are subject to slow change over time and with changes in temperature, input conditions, etc. Noise. Amplifiers generate random voltage at the outputs even when there is no signal applied. This can be due to thermal noise and flicker noise of the devices. For applications with high gain or high bandwidth, noise becomes a very important consideration. AC imperfections. The op-amp gain calculated at DC does not apply at higher frequencies. Thus, for high-speed operation, more sophisticated considerations must be used in an op-amp circuit design. Finite bandwidth. All amplifiers have finite bandwidth. To a first approximation, the op-amp has the frequency response of an integrator with gain. That is, the gain of a typical op-amp is inversely proportional to frequency and is characterized by its gain bandwidth productor, GBWP. For example, an op-amp with a GBWP of 1 MHz would have a gain of 5 at 200 kHz, and a gain of 1 at 1 MHz. This dynamic response coupled with the very high DC gain of the op-amp gives it the characteristics of a first-order low-pass filter with very high DC gain and low cutoff frequency given by the GBWP divided by the DC gain. The finite bandwidth of an op-amp can be the source of several problems, including stability. Associated with the bandwidth limitation is a phase difference between the input signal and the amplifier output that can lead to oscillation in some feedback circuits. For example, a sinusoidal output signal meant to interfere destructively with an input signal of the same frequency will interfere constructively if delayed by 180 degrees, forming positive feedback. In these cases, the feedback circuit can be stabilized by means of frequency compensation, which increases the gain or phase margin of the open-loop circuit. The circuit designer can implement this compensation externally with a separate circuit component. Alternatively, the compensation can be implemented within the operational amplifier with the addition of a dominant pole that sufficiently attenuates the high-frequency gain of the operational amplifier. The location of this pole may be fixed internally by the manufacturer or configured by the circuit designer using methods specific to the op-amp. In general, dominant pole frequency compensation reduces the bandwidth of the op-amp even further. When the desired closed-loop gain is high, op-amp frequency compensation is often not needed because the requisite open-loop gain is sufficiently low. Consequently, applications with high closed-loop gain can make use of op-amps with higher bandwidths. Noise, distortion, and other effects. Reduced bandwidth also results in lower amounts of feedback at higher frequencies, producing higher distortion, noise, and output's impedance, and also reduced output phase linearity as the frequency increases. Typical low-cost, general-purpose op-amps exhibit a GBWP of a few megahertz. Specialty and high-speed op-amps exist that can achieve a GBWP of hundreds of megahertz. For very high-frequency circuits, a current feedback operational amplifier is often used. Input capacitance, most important for high-frequency operation because it further reduces the open-loop bandwidth of the amplifier. Common mode gain, see DC imperfections, above. Nonlinear imperfections. Saturation, output voltage is limited to a minimum and maximum value close to the power supply voltages. Saturation occurs when the output of the amplifier reaches this value and is usually due to, in the case of an op-amp using a bipolar power supply, a voltage gain that produces an output that is more positive or more negative than that maximum or minimum. Or, in the case of an op-amp using a single supply voltage, either a voltage gain that produces an output that is more positive than that maximum, or a signal so close to ground that the amplifier's gain is not sufficient to raise it above the lower threshold. Slewing, the amplifier's output voltage reaches its maximum rate of change, the slew rate, usually specified in volts per microsecond. When slewing occurs, further increases in the input signal have no effect on the rate of change of the output. Slewing is usually caused by internal capacitances in the amplifier, especially those used to implement its frequency compensation. Nonlinear input-output relationship, the output voltage may not be accurately proportional to the difference between the input voltages. It is commonly called distortion when the input signal is a waveform. This effect will be very small in a practical circuit where substantial negative feedback is used. Phase reversal, in some integrated op-amps, when the published common mode voltage is violated, the output may slew to the opposite polarity from what is expected in normal operation. Under such conditions, negative feedback becomes positive, likely causing the circuit to lock up in that state. Power considerations, limited output current, the output current must be finite. In practice, most op-amps are designed to limit the output current so as not to exceed a specified level around 25 mA for a Type 741 IC op-amp thus protecting the op-amp and associated circuitry from damage. Modern designs are electronically more rugged than earlier implementations and some can sustain direct short circuits on their outputs without damage. Output sink current. The output sink current is the maximum current allowed to sink into the output stage. Some manufacturers show the output voltage versus the output sink current plot, which gives an idea of the output voltage when it is sinking current from another source into the output pin. Limited dissipated power. The output current flows through the op-amp's internal output's impedance, dissipating heat. If the op-amp dissipates too much power, then its temperature will increase above some safe limit. The op-amp may enter thermal shutdown, or it may be destroyed. Modern integrated FET or MOS-FET op-amps approximate more closely the ideal op-amp than bipolar ICs when it comes to input impedance and input bias currents. Bipolars are generally better when it comes to input voltage offset, and often have lower noise. Generally, at room temperature, with a fairly large signal, and limited bandwidth, FET and MOS-FET op-amps now offer better performance. Internal circuitry of 741 type op-amp. Sourced by many manufacturers, and in multiple similar products, an example of a bipolar transistor operational amplifier is the 741 integrated circuit designed by Dave Fulligar at Fairchild Semiconductor after Bob Widler's LM301 integrated circuit design. In this discussion, we use the parameters of the hybrid pi model to characterize the small signal, grounded emitter characteristics of a transistor. In this model, the current gain of a transistor is denoted HFE, more commonly called the I-squared. Architecture: a small-scale integrated circuit, the 741 op-amp shares with most op-amps an internal structure consisting of 3 gain stages. Differential amplifier Euro provides high differential amplification, with rejection of common mode signal, low noise, high input impedance, and drives a voltage amplifier Euro provides high voltage gain, a single pole frequency roll-off, and in turn drives the output amplifier Euro provides high current gain, along with output current limiting, and output short circuit protection. Additionally, it contains current mirror bias circuitry and a gain stabilization capacitor. Differential amplifier, a cascaded differential amplifier followed by a current mirror active load. The input stage is a transconductance amplifier, turning a differential voltage signal at the bases of Q1, Q2 into a current signal into the base of Q15. It entails 2 cascaded transistor pairs, satisfying conflicting requirements. The first stage consists of the matched NPN emitter follower pair Q1, Q2 that provide high input impedance. The second is the matched PNP common base pair Q3, Q4 that eliminates the undesirable Miller effect. It drives an active load Q7 plus matched pair Q5, Q6. That active load is implemented as a modified Wilson current mirror. Its role is to convert the input current signal to a single-ended signal without the attendant 50% losses. Thus, a small signal differential current in Q3 versus Q4 appears summed at the base of Q15, the input of the voltage gain stage. Voltage amplifier: the voltage gain stage consists of the 2 NPN transistors Q15/Q19 connected in a Darlington configuration and uses the output side of current mirror Q12/Q13 as its collector load to achieve its high voltage gain. The output sink transistor Q20 receives its base drive from the common collectors of Q15 and Q19. The level shifter Q16 provides base drive for the output source transistor Q14. Note the similarity between the transistors Q15 and Q7. The transistor Q22 prevents this stage from saturating by diverting the excessive Q15 base current. Output amplifier: the output stage is a Class AB push-pull emitter follower amplifier. It provides an output drive with impedance of a per mil 50 Ic copyright, in essence, current gain. Transistor Q16 provides the quiescent current for the output transistors, and Q17 provides output current limiting. Biasing circuits provide appropriate quiescent current for each stage of the op-amp. The resistor connecting the Q11 and Q12, and the given supply voltage, determine the current in the current mirrors, Q10/Q11 and Q12/Q13. The collector current of Q11, I1139 a key copyright equals versus plus of 0.2 VBE. For the typical versus equals A plus or minus 20 of E, the standing current in Q11/Q12 would be a per mil 1 mA. A supply current for a typical 741 of about 2 mA agrees with the notion that these two bias currents dominate the quiescent supply current. Transistors Q11 and Q10 form a Widler current mirror, with quiescent current in Q10 I10 such that Ln, I11/I10, equals I10 a key copyright/28 a megavolt, where 5 a key copyright represents the emitter resistor of Q10. and 28 MV is Vt, the thermal voltage at room temperature. In this case I10 per mil 20 AI1/4 A. Differential amplifier. The biasing circuit of this stage is set by a feedback loop that forces the collector currents of Q10 and Q9 to match. The small difference in these currents provides the drive for the common base of Q3/Q4. The summed quiescent currents of Q1/Q3 plus Q2/Q4 is mirrored from Q8 into Q9, where it is summed with a collector current in Q10, the result being applied to the bases of Q3/Q4. The quiescent currents of Q1/Q3 I1 will thus be half of I10, of order of per mil 10 AI1/4 A. Input bias current for the base of Q1 will amount to I1/I squared, typically a per mil 50 nanoampere, implying a current gain HFE a per mil 200 for Q1, Q2. This feedback circuit tends to draw the common base node of Q3/Q4 to a voltage VCOM at 2 VBE, where VCOM is the input common mode voltage. At the same time, the magnitude of the quiescent current is relatively insensitive to the characteristics of the components Q1/Q4, such as HFE, that would otherwise cause temperature dependence or part-to-part variations. Transistor Q7 drives Q5 and Q6 into conduction until their collector currents match that of Q1/Q3 and Q2/Q4. The quiescent current in Q7 is VBE/50 Ic copyright, about 35 I1/4 A, as is the quiescent current in Q15, with its matching operating point. Thus, the quiescent currents are pairwise matched in Q1/Q2, Q3/Q4, Q5/Q6, and Q7/Q15. Voltage amplifier. Quiescent currents in Q16 and Q19 are set by the current mirror Q12/Q13, which is running at a per mil 1 mA. Through some mechanism, the collector current in Q19 tracks that standing current. Output amplifier. In the circuit involving Q16, the 4.5 Ic copyright resistor must be conducting about 100 AI1/4 A, with the Q16 VBE roughly 700 MV. Then the VCB must be about 0.45 AV and VCE at about 1.0 AV. Because the Q16 collector is driven by a current source and the Q16 emitter drives into the Q19 collector current sink, the Q16 transistor establishes a voltage difference between Q14 base and Q20 base of a per mil 1 AV, regardless of the common mode voltage of Q14/Q20 base. The standing current in Q14/Q20 will be a factor exp, 100 MV/Vt, a per mil 36 smaller than the 1 mA quiescent current in the Class A portion of the op-amp. This standing current in the output transistors establishes the output stage in Class AB operation and reduces the crossover distortion of this stage. Small signal differential mode. A small differential input voltage signal gives rise, through multiple stages of current amplification, to a much larger voltage signal on output. Input's impedance. Because Q1 and Q3 form a Darlington pair, the small signal differential input impedance is of order 2 HFE, where high is the small signal input impedance of Q1 and Q3 and where HFE is the transistor small signal current gain. This contrasts with what would be the case with a simpler emitter-coupled pair input stage, where the differential input impedance is too high, a factor of I squared lower. A typical 741 op-amp has an input impedance to a €8 miles copyright. Differential amplifier. A differential voltage band at the op-amp inputs gives rise to a small differential current in the bases of Q1 and Q2 in a per mil band /. This differential base current causes a change in the differential collector current in each leg by I and HFE. Introducing the transconductance of Q1, GM equals HFE/high, the current at the base of Q15 is Van GM/2. This portion of the op-amp cleverly changes a differential signal at the op-amp inputs to a single-ended signal at the base of Q15, and in a way that avoids wastefully discarding the signal in either leg. To see how, notice that a small negative change in voltage at the inverting input drives it out of conduction, and this incremental decrease in current passes directly from Q4 collector to its emitter, resulting in a decrease in base drive for Q15. On the other hand, a small positive change in voltage at the non-inverting input drives this transistor into conduction, reflected in an increase in current at the collector of Q3. This current drives Q7 further into conduction, which turns on current mirror Q5/Q6. Thus, the increase in Q3 emitter current is mirrored in an increase in Q6 collector current, resulting also in a decrease in base drive for Q15. Besides avoiding wasting 3 dB of gain here, this technique decreases common mode gain and feed-through of power supply noise. Voltage amplifier: a current signal I at Q15's base gives rise to a current in Q19 of order II². This current signal develops a voltage at the bases of output transistors Q14/Q20 proportional to the high of the respective transistor. Output amplifier: output transistors Q14 and Q20 are each configured as an emitter follower, so no voltage gain occurs there. Instead, this stage provides current gain, equal to the HFE of Q14. The output's impedance is not zero, as it would be in an ideal op-amp, but with negative feedback it approaches zero at low frequencies. Overall open-loop voltage gain: the net open-loop small signal voltage gain of the op-amp involves the product of the current gain HFE of some 4 transistors. In practice, the voltage gain for a typical 741 style op-amp is of order 200,000, and the current gain, the ratio of input impedance to output's impedance, provides yet more gain. Other linear characteristics: small signal common mode gain: the ideal op-amp has infinite common mode rejection ratio, or zero common mode gain. In the present circuit, if the input voltages change in the same direction, the negative feedback makes Q3/Q4 base voltage follow the input voltage variations. Now the output part of Q10/Q11 current mirror keeps up the common current through Q9/Q8 constant in spite of varying voltage. Q3/Q4 collector currents, and accordingly the output current at the base of Q15, remain unchanged. In the typical 741 op-amp, the common mode rejection ratio is 90 dB, implying an open-loop common mode voltage gain of about 6. Frequency compensation: the innovation of the Fairchild I1/4 A741 was the introduction of frequency compensation via an on-chip capacitor, simplifying application of the op-amp by eliminating the need for external components for this function. The 30 pF capacitor stabilizes the amplifier via Miller compensation and functions in a manner similar to an op-amp integrator circuit. Also known as dominant pole compensation because it introduces a pole that masks the effects of other poles into the open-loop frequency response. In a 741 op-amp this pole can be as low as 10 Hz. This internal compensation is provided to achieve unconditional stability of the amplifier in negative feedback configurations where the feedback network is non-reactive and the closed-loop gain is unity or higher. By contrast, amplifiers requiring external compensation, such as the I1/4 A748, may require external compensation or closed-loop gain significantly higher than unity. Input offset voltage: the offset null pins may be used to place external resistors in parallel with the emitter resistors of Q5 and Q6, to adjust the balance of the Q5/Q6 current mirror. The potentiometer is adjusted such that the output is null when the inputs are shorted together. Nonlinear characteristics: input breakdown voltage: the transistors Q3, Q4 help to increase the reverse VBE rating. The base emitter junctions of the NPN transistors Q1 and Q2 break down at around 7 V, but the PNP transistors Q3 and Q4 have VBE breakdown voltages around 50 V. Output stage voltage swing and current limiting: variations in the quiescent current with temperature, or between parts with the same type number, are common, so crossover distortion and quiescent current may be subject to significant variation. The output range of the amplifier is about 1 volt less than the supply voltage, owing in part to VBE of the output transistors Q14 and Q20. The 25I copyright resistor at the Q14 emitter, along with Q17, acts to limit Q14 current to about 25 mA. Otherwise, Q17 conducts no current. Current limiting for Q20 is performed in the voltage gain stage. Q22 senses the voltage across Q19's emitter resistor. As it turns on, it diminishes the drive current to Q15 base. Later versions of this amplifier schematic may show a somewhat different method of output current limiting. Applicability considerations. Note, while the 741 was historically used in audio and other sensitive equipment, such use is now rare because of the improved noise performance of more modern op-amps. Apart from generating noticeable hiss, 741s and other older op-amps may have poor common mode rejection ratios and so will often introduce cable-borne mains hum and other common mode interference, such as switch clicks, into sensitive equipment. The 741 has come to often mean a generic op-amp IC. The description of the 741 output stage is qualitatively similar for many other designs, except, some devices are not internally compensated. Some modern devices have rail-to-rail output capability, meaning that the output can range from within a few millivolts of the positive supply voltage to within a few millivolts of the negative supply voltage. Classification. Op-amps may be classified by their construction: discrete, IC most common, hybrid, IC op-amps may be classified in many ways, including, military, industrial, or commercial grade. This may define operating temperature ranges and other environmental or quality factors. Classification by package type may also affect environmental hardiness, as well as manufacturing options. DIP, and other through-hole packages are tending to be replaced by surface mount devices. Classification by internal compensation. Op-amps may suffer from high-frequency instability in some negative feedback circuits unless a small compensation capacitor modifies the phase and frequency responses. Op-amps with a built-in capacitor are termed compensated, or perhaps compensated for closed-loop gains down to 5. All others are considered uncompensated. Single, dual and quad versions of many commercial op-amp IC are available, meaning 1, 2 or 4 operational amplifiers are included in the same package. Rail-to-rail input op-amps can work with input signals very close to the power supply rails. CMOS op-amps provide extremely high input resistances, higher than JFET input op-amps, which are normally higher than bipolar input op-amps. Other varieties of op-amp include programmable op-amps. Manufacturers often tabulate their op-amps according to purpose, such as low-noise preamplifiers, wide-bandwidth amplifiers, and so on. Applications. Use in electronic system design. The use of op-amps as circuit blocks is much easier and clearer than specifying all their individual circuit elements, whether the amplifiers used are integrated or discrete. In the first approximation, op-amps can be used as if they were ideal differential gain blocks. At a later stage, limits can be placed on the acceptable range of parameters for each op-amp. Circuit design follows the same lines for all electronic circuits. A specification is drawn up governing what the circuit is required to do, with allowable limits. For example, the gain may be required to be 100 times, with a tolerance of 5% but drift of less than 1% in a specified temperature range. The input's impedance not less than 1 megohm, etc. A basic circuit is designed, often with the help of circuit modeling. Specific commercially available op-amps and other components are then chosen that meet the design criteria within the specified tolerances at acceptable cost. If not all criteria can be met, the specification may need to be modified. A prototype is then built and tested. Changes to meet or improve the specification, alter functionality, or reduce the cost, may be made. Applications without using any feedback, that is, the op-amp is being used as a voltage comparator. Note that a device designed primarily as a comparator may be better if, for instance, speed is important or a wide range of input voltages may be found, since such devices can quickly recover from full-on or full-off states. A voltage level detector can be obtained if a reference voltage VOF is applied to one of the op-amp's inputs. This means that the op-amp is set up as a comparator to detect a positive voltage. If the voltage to be sensed, i.e., is applied to op-amp's input, the result is a non-inverting positive level detector, when I is above RF. VO equals plus Vsat. When early is below VRF, VO equals Vsat. If early is applied to the inverting input, the circuit is an inverting positive level detector. When early is above VRF, VO equals Vsat. A zero voltage level detector can convert, for example, the output of a sine wave from a function generator into a variable frequency square wave. If early is a sine wave, triangular wave, or wave of any other shape that is symmetrical around zero, the zero-crossing detector's output will be square. Zero-crossing detection may also be useful in triggering TRIACs at the best time to reduce mains interference and current spikes. Positive feedback applications. Another typical configuration of op-amps is with positive feedback, which takes a fraction of the output signal back to the non-inverting input. An important application of it is the comparator with hysteresis, the Schmitt trigger. Some circuits may use positive feedback and negative feedback around the same amplifier, for example triangle wave oscillators and active filters. Because of the wide slew range and lack of positive feedback, the response of all the open-loop level detectors described above will be relatively slow. External overall positive feedback may be applied, but this markedly affects the accuracy of the zero-crossing detection point. Using a general-purpose op-amp, for example, the frequency of early for the sine-to-square wave converter should probably be below 100 Hz. Negative feedback applications, non-inverting amplifier. In a non-inverting amplifier, the output voltage changes in the same direction as the input voltage. The gain equation for the op-amp is. However, in this circuit VAR is a function of out because of the negative feedback through the A1 A2 network. A1 and A2 form a voltage divider, and as VAR is a high impedance input, it does not load it appreciably. Consequently, where substituting this into the gain equation, we obtain solving for. If is very large, this simplifies to. The non-inverting input of the operational amplifier needs a path for DC to ground. If the signal source does not supply a DC path, or if that source requires a given load impedance, then the circuit will require another resistor from the non-inverting input to ground. When the operational amplifier's input bias currents are significant, then the DC source resistances driving the inputs should be balanced. The ideal value for the feedback resistors will be such that the two resistances in parallel roughly equal the resistance to ground at the non-inverting input pin. That ideal value assumes the bias currents are well matched, which may not be true for all op-amps. Inverting amplifier. In an inverting amplifier, the output voltage changes in an opposite direction to the input voltage. As with the non-inverting amplifier, we start with the gain equation of the op-amp. This time, VAR is a function of both Vout and VAN due to the voltage divider formed by RF and RIN. Again, the op-amp input does not apply an appreciable load, so substituting this into the gain equation and solving for if is very large, this simplifies to a resistor is often inserted between the non-inverting input and ground, reducing the input offset voltage due to different voltage drops due to bias current, and may reduce distortion in some op-amps. A DC blocking capacitor may be inserted in series with the input resistor when a frequency response down to DC is not needed and any DC voltage on the inputs is unwanted. That is, the capacitive component of the input's impedance inserts a DC 0 and a low-frequency pole that gives the circuit a bandpass or high-pass characteristic. The potentials at the operational amplifier inputs remain virtually constant in the inverting configuration. The constant operating potential typically results in distortion levels that are lower than those attainable with a non-inverting topology. Other applications, audio and video frequency preamplifiers and buffers, differential amplifiers, differentiators and integrators, filters, precision rectifiers, precision peak detectors, voltage and current regulators, analog calculators, analog to digital converters, digital to analog converters, voltage clamping, oscillators and waveform generators. Most single, dual and quad op-amps available have a standardized pinout which permits one type to be substituted for another without wiring changes. A specific op-amp may be chosen for its open-loop gain, bandwidth, noise performance, inputs impedance, power consumption, or a compromise between any of these factors. Historical timeline: 1941, a vacuum tube op-amp. An op-amp, defined as a general-purpose, DC-coupled, high-gain, inverting feedback amplifier, is first found in U.S. Patent 2,401,779 summing amplifier filed by Carl D. Schwartzel Jr. of Bell Labs in 1941. This design used 3 vacuum tubes to achieve a gain of 90 decibels and operated on voltage rails of A plus or minus 350 V. It had a single inverting input rather than differential inverting and non-inverting inputs, as are common in today's op-amps. Throughout World War II, Schwartzel's design proved its value by being liberally used in the M9 artillery director designed at Bell Labs. This artillery director worked with the 584-seat LOS Rupees radar system to achieve extraordinary hit rates that would not have been possible otherwise. 1947, an op-amp with an explicit non-inverting input. In 1947, the operational amplifier was first formally defined and named in a paper by Professor John Aragazni of Columbia University. In this same paper, a footnote mentioned an op-amp designed by a student that would turn out to be quite significant. This op-amp, designed by Louis B. Julie, was superior in a variety of ways. It had 2 major innovations. Its input stage used a long-tailed triode pair with loads matched to reduce drift in the output and, far more importantly, it was the first op-amp designed to have 2 inputs. The differential input made a whole range of new functionality possible, but it would not be used for a long time due to the rise of the chopper-stabilized amplifier. 1949, a chopper-stabilized op-amp. In 1949, Edwin A. Goldberg designed a chopper-stabilized op-amp. This setup uses a normal op-amp with an additional AC amplifier that goes alongside the op-amp. The chopper gets an AC signal from DC by switching between the DC voltage and ground at a fast rate. This signal is then amplified, rectified, filtered and fed into the op-amp's non-inverting input. This vastly improved the gain of the op-amp while significantly reducing the output drift and DC offset. Unfortunately, any design that used a chopper couldn't use their non-inverting input for any other purpose. Nevertheless, the much improved characteristics of the chopper-stabilized op-amp made it the dominant way to use op-amps. Techniques that used the non-inverting input regularly would not be very popular until the 1960s when op-amp ICs started to show up in the field. 1953, a commercially available op-amp. In 1953, vacuum tube op-amps became commercially available with the release of the Model K2W from George A. Philbrick Researches, Incorporated. The designation on the devices shown, GAP-R, is an acronym for the complete company name. 2 9-pin 12AX7 vacuum tubes were mounted in an octal package and had a Model K2P chopper add-on available that would effectively use up the non-inverting input. This op-amp was based on a descendant of Louis B. Julie's 1947 design and, along with its successors, would start the widespread use of op-amps in industry. 1961, a discrete IC op-amp. With the birth of the transistor in 1947, and the silicon transistor in 1954, the concept of ICs became a reality. The introduction of the planar process in 1959 made transistors and ICs stable enough to be commercially useful. By 1961, solid-state, discrete op-amps were being produced. These op-amps were effectively small circuit boards with packages such as edge connectors. They usually had hand-selected resistors in order to improve things such as voltage offset and drift. The P45 had a gain of 94 decibel and ran on A plus or minus 15 of V rails. It was intended to deal with signals in the range of A plus or minus 10 V. 1961, a Varactor bridge op-amp. There have been many different directions taken in op-amp design. Varactor bridge op-amps started to be produced in the early 1960s. They were designed to have extremely small input current and are still amongst the best op-amps available in terms of common mode rejection with the ability to correctly deal with hundreds of volts at their inputs. 1962, an op-amp in a potted module. By 1962, several companies were producing modular potted packages that could be plugged into printed circuit boards. These packages were crucially important as they made the operational amplifier into a single black box which could be easily treated as a component in a larger circuit. 1963, a Monolithic Ic Op-Amp. In 1963, the first Monolithic Ic Op-Amp, the I-1/4 A702 designed by Bob Widler at Fairchild Semiconductor, was released. Monolithic ICs consist of a single chip as opposed to a chip in discrete parts or multiple chips bonded and connected on a circuit board. Almost all modern op-amps are monolithic ICs. However, this first IC did not meet with much success. Issues such as an uneven supply voltage, low gain and a small dynamic range held off the dominance of monolithic op-amps until 1965 when the I-1/4 A709 was released. 1968, release of the I-1/4 A741. The popularity of monolithic op-amps was further improved upon the release of the LM101 in 1967, which solved a variety of issues, and the subsequent release of the I-1/4 A741 in 1968. The I-1/4 A741 was extremely similar to the LM101 except that Fairchild's facilities allowed them to include a 30 APF compensation capacitor inside the chip instead of requiring external compensation. This simple difference has made the 741 the canonical op-amp and many modern amps base their pin-out on the 741s. The I-1/4 A741 is still in production, and has become ubiquitous in electronics. Many manufacturers produce a version of this classic chip, recognizable by part numbers containing 741. The same part is manufactured by several companies. 1970, first high-speed, low-input current FET design. In the 1970s high-speed, low-input current designs started to be made by using FETs. These would be largely replaced by op-amps made with MOS FETs in the 1980s. During the 1970s single-sided supply op-amps also became available. 1972, single-sided supply op-amps being produced. A single-sided supply op-amp is one where the input and output voltages can be as low as the negative power supply voltage instead of needing to be at least 2 volts above it. The result is that it can operate in many applications with the negative supply pin on the op-amp being connected to the signal ground, thus eliminating the need for a separate negative power supply. The LM324 was one such op-amp that came in a quad package and became an industry standard. In addition to packaging multiple op-amps in a single package, the 1970s also saw the birth of op-amps in hybrid packages. These op-amps were generally improved versions of existing monolithic op-amps. As the properties of monolithic op-amps improved, the more complex hybrid ICs were quickly relegated to systems that are required to have extremely long service lives or other specialty systems. Recent trends. Recently supply voltages in analog circuits have decreased and low-voltage op-amps have been introduced reflecting this. Supplies of A plus or minus 5 of E and increasingly 3.3 of E are common. To maximize the signal range, modern op-amps commonly have rail-to-rail output and sometimes rail-to-rail inputs. See also: operational amplifier applications, differential amplifier, instrumentation amplifier, active filter, current feedback operational amplifier, operational transconductance amplifier, George A. Philbrick, Bob Widler, analog computer, negative feedback amplifier, current conveyor, notes. References. Further reading, Design with Operational Amplifiers and Analog Integrated Circuits. 4th ed. Sergio Franco. McGraw-Hill. 672 pages. 2014. ISBN 978-0078028168. Op-Amps for Everyone. 4th ed. Ron Mancini. Neumes. 304 pages. 2013. ISBN 978-0123914958. Small Signal Audio Design. Douglas Self. Focal Press. 556 pages. 2010. ISBN 978-0-240-52177-0. Op-Amp Applications Handbook. Walt G. Young. Nunes. 896 pages. 2004. ISBN 978-0750678445. Op-Amps and Linear Integrated Circuits. James M. Thiel. Cengage Learning. 616 pages. 2000. ISBN 978-0766817937. Operational Amplifiers and Linear Integrated Circuits. 6th ed. Robert F. Corlin. Prentice Hall. 529 pages. 2000. ISBN 978-0130149916. Op-Amps and Linear Integrated Circuits. 4th ed. Ramgar Awkward. Prentice Hall. 543 pages. 1999. ISBN 978-0132808682. Basic Operational Amplifiers and Linear Integrated Circuits. 2nd ed. Thomas L. Floyd and David Buckler. Prentice Hall. 593 pages. 1998. ISBN 978-0130829870. Troubleshooting Analog Circuits. Bob Pease. Nunes. 217 pages. 1991. ISBN 978-0750694995. IC Op-Amp Cookbook. 3rd ed. Walter G. Young. Prentice Hall. 433 pages. 1986. ISBN 978-0138896010. Engineer's Mini Notebook and a Euro Op-Amp IC Circuits. Forrest Mims 3. Radio Shack. 49 pages. 1985. A Scene B000DZG196. External links, simple op-amp measurements. How to measure offset voltage, offset and bias current, gain, CMRR, and PSRR. Introduction to op-amp circuit stages, second-order filters, single op-amp bandpass filters, and a simple intercom, MOS op-amp design, a tutorial overview, operational amplifier noise prediction using spot noise, operational amplifier basics, history of the op-amp from vacuum tubes to about 2002. Lots of detail, with schematics. IC part is somewhat ADI-centric. Louis B. Julie Historical Op-Amp interview by Bob Pease, www.philbrickarchive.org. A free repository of materials from George A. Philbrick/researchers, Operational Amplifier Pioneer, HOTA unregistered trademark. The difference between operational amplifiers and instrumentation amplifiers. Electronic Design Magazine, IC Data Sheets, LM301, Single BJT Op-Amp, Texas Instruments, LM324, Quad BJT Op-Amp, Texas Instruments, LM741, Single BJT Op-Amp, Texas Instruments, Nebraska, 5532, Dual BJT Op-Amp, Texas Instruments, TLO72, Dual JFET Op-Amp, Texas Instruments,